All right, I'm going to talk about poles of Eisenstein series, but also this is going to be a useful exercise in looking stuff up carefully. So when I say poles of Eisenstein series, what I mean is that we're going to have an Eisenstein series, Zs chi, and I'm going to consider specifically the Eisenstein series at the cusp infinity. You can do the same thing for the cusp zero, but I'm going to do it just for the cusp infinity for this example. And we saw that if chi is non-trivial, then that implies that our Eisenstein series, where I'm just going to write E Zs chi, and at the cusp infinity, sometimes written with just infinity and the I omitted, has no poles. So we're only going to be interested in the case where chi is trivial. So here, to reiterate, EZS, and I'm going to write chi naught, is going to be weight 0 level n. And here, when I write chi naught, I mean the trivial character mod n. And so what are the poles of this? It turns out this is going to have one pole at s equals 1, but how do we figure that out? So the plan is going to be to write down a Fourier expansion for this. And then when we have a Fourier expansion, we can just look at each of the individual terms and see which terms have poles and what the residues are, and get all the information that way. So to write down the Fourier expansion, I'll use the same reference that I've recommended before, which is this paper of Matthew Young from 2019 called Explicit Calculations with Eisenstein Series. Now, there you have to be a little bit careful. There's a lot of notation in that paper, and you need to make sure that what you're looking up is exactly the thing that you want. So let me show you how I would do that for this objective of getting the Fourier expansion of an Eisenstein series with trivial character. Well, the general idea in Young's paper is that he has two types of Eisenstein series. He has E attached to cusps, and he has Eisenstein series attached to characters. And we talked about this previously. The main idea is that the Eisenstein series attached to cusps tend to be the thing that people care about for applications, the things that people normally talk about. But when you're actually, say, looking up Fourier expansions, they're much nicer when you write them down using this language of Eisenstein series attached to characters. And so Young does all his stuff with Eisenstein series attached to characters and then gives you formulas for translating from characters to cusps, as well as formulas from translating from cusps to characters if you want to do that, but I haven't had to do that yet. So let's start looking stuff up. So the first thing, and this isn't quite the order that you do it in, but the first thing that is going to be relevant is that in section 3.1, he writes down the following. Let me see if I can get this right. Why is that way over there? So he writes down the following. And from this, the main takeaway is that the reason why I'm copy-pasting this paragraph is because we need to know what we're going to need to know what the Dirichlet character psi is. So psi is just a character mod n. And there are no other assumptions on chi. So for example, or on psi. So psi is not assumed to be primitive, for example. Later on, certain characters are assumed to be primitive, but this one is not. And the other thing that I want to highlight from this same section is the following blurb. So here, Young is explicitly saying that minus the identity is in your group gamma naught n, and therefore blah, blah, blah. This tells us that we're really working in SL2Z, not PSL2Z. And this is an important thing to check, because if you're working in one instead of the other, that can give you a factor of 2 somewhere. And it can be dangerous because maybe you're getting some of your formulas from one reference and some of your formulas from another reference, and then one is secretly working in PSL2Z and the other one's working in SL2Z, and then you've got a factor of 2 mismatch and you don't end up getting what you should be getting. So you should always check if the author is working with SL2Z or PSL2Z. Okay, so this does not explicitly say that he's working in SL2Z, but of course, it would make no sense to mention that minus I is in the group if you're working in PSL2Z. So that's sufficient for this. Now, the next thing to look up in this paper is going to be this following blurb. So here there's a lot of blah blah, but the main point is that your cusps are going to be 1 over W, and the notation is going to be that is 1 over U times F, where F divides N, and U is mod the GCD of F and N over F. And then the rest of the stuff, is interesting, but it's not important for what we're going to be doing. But this is the stuff that we want. So remember, for example, if n is prime, the level n, then you only have 2 cusps, 1 over 1 and 1 over n. This was discussed previously. Okay, so we're going to end up needing this fact. And the next fact that we're going to end up needing is, fact is maybe a strong word. The next part of the notation that we're going to end up needing from this paper is this proposition. So here, this is just a definition of n prime, w prime, and n prime prime, and double prime. And then finally, the main result that we're going to make use of to write down our Fourier expansion is the following. Okay, so this is some big mess, but this is the main formula that we're going to need. And of course, when I actually went and looked this stuff up, I did it in sort of the reverse order, right? Because I found theorem 6.1, which sure looks like the thing I'm going to need. And it says, okay, let the notation be as in section 5.2. Okay, let's go check section 5.2. We've got this f, this n double prime, so we needed this proposition, we needed this stuff. And then I also saw this psi right here and said, oh, what's psi? Are there any assumptions about psi? And so that's why I needed to go and get this fact. So in practice, this happens backwards, but this is the end result. And let's see what this actually gives us in a simple case. So I'm going to further assume that n is prime. Maybe you can you can guess that it's maybe this is enough of a mess that we don't need to think about other cases yet. And I'm also going to assume that psi is chi naught. So remember, this was the trivial character mod n, right? Because as we discussed at the beginning of this lecture, if psi is not trivial here, then you just don't get a pole at all. So this is the case to consider. So what does this end up giving us? Well, let's first look at the consequences of assuming that n is prime. So we have our cusps 1 over 1 and 1 over n. This cusp is the cusp infinity, this cusp is the cusp 0. And that means that w is either 1 or n in this notation. And that implies that f is w and u is 1. Here f and u are these things. 1 over w is 1 over uf, and u has to be mod f, mod the GCD of f and n over f. So if f is 1, then it's the GCD of 1 and n, which is 1. If f is n, then it's the GCD of n and 1, which is also 1. So in both cases, u is 1 and w is f. Okay? And now we need to figure out what n prime, w prime, and n double prime are. So n prime, you've got two cases to work out, and you end up finding that n prime is always n over w. You find that w prime is 1, again just going case by case, because there are only two cases. And you find that nw prime is also equal to n over w. Okay? So now let's look at our Fourier expansion and see what's going to happen. So we're going to be interested in the case where f is n, because as I said at the beginning, I'm only going to look at the Fourier expansion at infinity. So that's the case where w is n. So the Fourier expansion of E at 1 over n zs chi 0 per this formula, what's going to happen with these sums? Well, f is going to be w, so q1 and w is going to be n. So q1 is necessarily 1, so this sum is not going to appear. And this term here, this phi is the Euler-Toscan function, and this argument is 1, as we discussed previously, so this term is not going to appear. So what do we end up getting? We end up getting, so far, that this first term, f n double prime to the s in the denominator, that ends up giving us n to the s over n to the 2s. Obviously, you can cancel. And then the next term is 1, and then you have a sum over q2 divides n, because here q2 is dividing f, and f was w, and w was n. And then we have a sum marked with an asterisk of chi1, chi2, and the assumptions on chi1 and chi2 are that chi1 has to be primitive mod q1. Well, q1 was 1, so chi1 is just a trivial character. Now, chi2 is a primitive character mod q2, and if q2 is n, then the product chi1, chi2 is a primitive character mod n, but we need that character to be induced by the same character as psi, and psi is the trivial character, so is induced by the trivial character mod 1. And so this condition here, this bottom condition that the product chi1 chi2 bar has to be induced by the same character as psi, means that in fact q2 has to be 1. So what we end up finding is chi1 chi2 bar being induced by the same character as psi in fact implies that q2 is 1. Okay, so let's write down our Fourier expansion again. So here we can write our Fourier expansion is n to the 1 over n to the s, and again q2 has to be 1, so we can just omit that. And then our sum over characters of, well, we don't really have many choices, right? Because both q1 and q2 are 1, so this is just the trivial character, so there's really no sum here at all. And then we have the trivial character evaluating minus 1, I mean that's 1. And then, so here's the first actual thing that we get. So this is the this is the Riemann zeta function at 2s, and then in the denominator we have the Dirichlet L function, L2s chi naught. Next we have a sum over a divides n, with the GCD of a and 1 being 1, so this is automatic, so just the sum over a divides n. And b is going to divide 1, so there's really no sum over b here. So the sum a divides n, and then the terms that we get are, we have a mu a, and then mu b is just 1, and then we have this chi1b never appears because b is 1, so we have a chi2a, but chi2 is trivial, so this doesn't appear either, and then we have an a to the s in the denominator, so we get mu a over a to the s, and then finally we have our Eisenstein series in terms of characters, where both characters here are the trivial character. And then we're evaluating it at b times f. F was w, w was n, so it's n divided by a times z, comma s. Okay, so this is what we get as when we express our Eisenstein series at the cusp infinity in terms of Eisenstein series twisted by characters. But this sum is, again, we're assuming that n is prime, has two terms in it. So let us just write that down explicitly. Maybe first, before doing that, it'd be good to write down what this ratio is. So it turns out that the ratio zeta 2s divided by L 2s chi naught is equal to 1 minus n to the minus 2s to the minus 1. And so why is this? Well, this Riemann zeta function, you can write it as a product, you can write it in terms of the Euler product, right? So it's a product over primes of 1 minus p to the s, or sure this will be for zeta of s, to the minus 1. And then in the denominator we have the same Euler product, but here it's 1 minus chi naught of p to the minus s to the minus 1. And chi naught, the trivial character mod n, is going to be 1 for every prime except when you have p equal to n. So when p equals n, then this here is 0. So this is 1 if p is not equal to n, and 0 if p is equal to n. And when it's 0, then you just don't have this term, and you have just a 1 here. So what that means is that this ratio of Euler products, every factor except the p equals n factor cancels out, and you're left just with 1 minus n to the minus s to the minus 1. So that's why this ratio is this. Sometimes people will write, they'll use the notation for the Dirichlet series with Euler product with certain factors removed. They'll write it as zeta, and then they'll put a superscript in parentheses like this to mean you're just removing the Euler product, the factors in the Euler product, for which p divides n. So that's just some notation that you might see. Okay, so let's rewrite this, but writing out explicitly what we have since we only have two terms. So e, and then here I'm going to write infinity, zs chi naught equals 1 over n to the s, and then we have, going to put this in the denominator, 1 minus n to the minus 2s. And then, okay, when a is 1, what do we end up getting? This coefficient in front is just 1, so we have e1, 1, and then here we have an nzs, right, is it's just n, and then for the other term we have a minus sign, because this this mu of a is going to be mu of n is assumed to be prime, so the Mobius function evaluated there is minus 1, and we have an n to the s in the denominator, so we get n to the minus s, e1, 1, and then here we just have zs. Okay, so that's the expression that we get, and we can clean this up a little bit by, say, distributing this if we want to. Another reference for this, which is pretty specific for this specific kind of Fourier expansion, and a nice exposition that's pretty different from the others and to the point, is this paper of Templier about Huygner points. I forget the title exactly, but it involves Huygner points, and it is section 6 in that paper, where he gives the same type of formula and explains it from a different perspective. Okay, so we have this Eisenstein series. So of course now we need to know the Fourier expansion of this E11. So let's do that. So on, whoopsie-daisies. So on page 6 of Young's paper, he gives the following formula. Okay, kind of a mess, but it's going to be good enough for our purposes. So here, notice that there's this assumption that the chi's have to be primitive. Here, we're going to have just the trivial character mod 1. So what we end up getting for this is, and he says if the weight is 0, which is the case that we're in, then we have this. So we're going to have that this completed Eisenstein series E star, and then we'll figure that out later. Why is this not working? Okay, so we have our E star 1, 1 at ZS is going to be, and now let's write down what our constant term is. So Q1 and Q2 for us are both going to be 1, so we have both of these terms. And then we have a Q2 to the 2s, well, Q2 is 1, so this doesn't appear. We don't have this I to the minus k, so our k is 0, and we don't have our Gauss sum because chi2 is trivial. So what we end up getting is just gamma of s over pi to the s. Then we have our zeta function, zeta to s, y to the s as our first term. And then the second term is going to be the same thing, but at 1 minus s. And then the Fourier series stuff is going to be as follows. So it's going to be sum n not equal to 0, and then 2. And then here, okay, I'll write out exactly how to get it in this form in a moment, but you end up getting n to the 1/2 minus s, sum of divisors function at 2s minus 1 of n. Remember, we're defining this to be the same as the function evaluated at the absolute value of n. And then we have our Whittaker function, square root y times modified Bessel function of the second kind. And then here e of nx. So remember, I'm using the notation that e of nx is defined to be e to the 2 pi I nx. Okay, so this is what we end up getting. How did I get this form right here when it's written as lambda? Let me show you that quickly. So here, what Young gives is the sum of AB equals n, and this is a product over I guess he doesn't say it's a product over positive integers, but I sure hope it is, and equals the absolute value of n. So I'm just going to write n for simplicity, assume that n is positive. We've got no characters here, and we have a b over a to the s minus 1/2. And we can instead write this as a sum over b divides n, and then a is going to be n over b. So what we end up getting is b divided by n over b to the s minus 1/2, and then of course here we can just do some elementary manipulations, and we get n to the 1/2 minus s times the sum b divides n of b to the 2s minus 1, which is exactly what was written above, n to the 1/2 minus s sigma 2s minus 1 of n. Okay, so that's how I took this formula and rewrote it in this way. So we've got this Fourier expansion for the completed Eisenstein series, but we need this without the completed stuff, because that's the version that we have appearing in the thing that we want. So the last thing we're going to need is this definition of the completed Eisenstein series, and Young gives this directly above. So what's this going to be in our case? Well, just writing out what we get. Is going to be equal to, right, we have no Q2, we have no I to the k, and we have no Gauss sum. So we just end up getting Okay. So this is what we end up with. And what that's going to imply is that our Eisenstein series at the cusp of infinity is going to be equal to y to the s plus, and now here we have this gamma of 1 minus s over gamma of s, and then we have a pi to the s over pi to the 1 minus s, and then we have a zeta of 2 minus 2s over zeta of 2s, y to the 1 minus s, and then we have our Fourier expansion. Maybe it's better to factor out this term we get from completing. So the term that we get from completing, so we have a pi to the s over gamma s zeta 2s sum n not equal to 0 to absolute value n to the 1 half minus s sigma 2s minus 1 of n, and then times our Whittaker function. Okay. So this is the Fourier expansion that, oh man, not quite. This is the Fourier expansion we get for our without, still at level 1, not at level n. Yeah, sorry about that. Okay. Right, because we found that the completed version was this, and now we're just dividing by this factor in front. So recall that we had this formula. I should probably clean this up, sorry. So we have this formula, and we're interested in the poles of these things. We don't need to, at this point, write out exactly what the full Fourier expansion of this thing is. We can, by inspection, find the poles. So let's ask, where are the poles? I'm also going to clean this up a little bit. So instead of this factor here, I'm going to write it as 1 over n to the s plus n to the minus s. Make sure I didn't drop a minus sign or something. I did drop a minus sign. Good thing I checked. Okay. So let's look at the poles that we're getting here. So let's go term by term in the Fourier expansion. And we're only going to be interested in the poles for the real part of s at least 1. And the only pole that we're going to find is when s is exactly 1. So, all right, does this term, y to the s, have any poles? No. What about here? Well, we're going to get a pole when s is 1 coming from this gamma function. Gamma has no zeros, so we don't have to worry about this. We don't have to worry about these terms. When the real part of s is at least 1, this isn't going to have any poles. This isn't going to have any poles. or any zeros. And this y to the 1 minus s isn't going to have any poles. This factor in front is not going to have any poles. This stuff is not going to have any poles. And our Whittaker function is not going to have any poles. So the only pole comes from the gamma of 1 minus s. So the only pole of, I should say, E11, and I'll specify again with the real part of s is at least 1, comes from the gamma of 1 minus s. And as you can look up on Wikipedia, for instance, the residue at s equals 0 of gamma of s is 1. So that means the residue of this is going to be minus 1, since we have a minus s. So what is the residue we get for the whole thing? So the residue at s equals 1 of this term is going to be equal to, well, here, as we said, is going to be, we're going to have a minus 1, and then we're going to have over a gamma of 1, and then we have a pi over pi to the 0, zeta of 2, zeta of 0 over zeta of 2. And here we have a y to the 0. And now let's just plug in the values that we know for this. So gamma of 1 is 1, and then we have a pi here, and then zeta of 0 is minus 1/2, which you can figure out using the functional equation if you like, but it's also just well known. And then here, zeta of 2 is pi squared over 6, and then of course we don't have our y. And cleaning this up a little bit, we get value of pi over 3, right? Where is it? I am suspicious. Sorry, we get a 3 over pi. That's right. Okay. Okay. And great. So this is the that's the residue of that Eisenstein series, and this is the residue of the level 1 Eisenstein series, which is useful to know. So now let's use this formula. So that implies that the residue at s equals 1 of our Eisenstein series zs chi naught is equal to 1 over n minus n inverse, and then the residue of whatever this thing is. So here there was there's no z dependence in the residue, and I mean the pole that we were getting, there's no z dependence in that function. So the fact that we have an nz instead of z here doesn't matter for the residue, and we're just going to get 3 over pi here for the residue, and here we have an n to the minus 1 times 3 over pi. And so what do we end up getting? We end up getting I'm suspicious again. Okay, yes, no, okay, yeah, this is right. So we get a 1 minus an inverse over n minus an inverse times 3 over pi. And let's clean this up a little bit. So if we, I mean, just going to make the manipulations that look like they make most sense to me. N minus 1 over n squared minus 1 times 3 over pi, and then this is going to be 3 over pi times 1 over n plus 1. Cool. So this is sort of what we get for our residue. This is our final answer, that this is equal to that. And this is great. This is good to know, and it comes up a lot. One thing I will highlight is that, and this initially seems perhaps totally disconnected, is that the volume of SL2Z quotienting the upper half plane. And when I write this, what I mean is if you integrate the upper half plane mod SL2Z, so the standard fundamental domain, and then just using the usual metric. So here we're imagining this fundamental domain, so from minus 1/2 to 1/2, and then this is the line, absolute value of z is 1, so this is a semicircle, and this is the fundamental domain. And using just elementary calculus, right, you'll find that this gives you pi over 3. And now let's ask about the volume of gamma naught n quotienting the upper half plane. And one way to do this is to say that you just have a copy of this SL2Z fundamental domain for each element, for each coset, right? So this is going to be the index gamma naught 1, which is SL2Z. And it's the index of gamma naught n in gamma naught 1 times the volume of the upper half plane mod SL2Z. And we saw elsewhere that this quantity was n times the product of primes dividing n of 1 plus 1 over p. Hopefully it's 1 over p. Hopefully it's a plus here. If we get the wrong answer, I'll just go back and fix it. So, and then this we just said was pi over 3. Now, when n is prime, what we end up getting is going to be n times 1 plus 1 over n times pi over 3, which is equal to pi over 3 times n plus 1. Okay? And now let's look at our residue. That's cool. So what we've shown, and it seems like this is just pure coincidence, is that the residue at s equals 1 of our Eisenstein series at infinity of level n with trivial character is equal to 1 over the volume of the upper half plane mod gamma naught n, which is, I think it's kind of neat. If you want a different reference for this, you can look at Ivaniech, his spectral methods textbook, proposition 6.13.